So we are going to find the sum from n equals 1 to infinity of 1 over n squared plus n. But instead of using the normal telescoping strategy, we're going to try Taylor series. Now to start out, we'll do the standard trick, which is to factor the denominator. So we get the sum from n equals 1 to infinity of 1 over, and then we take out an n. That leaves us with n plus 1. Now I'm going to present a Taylor series. The natural log of 1 plus x equals the sum from n equals 1 to infinity of negative 1 to the n plus 1 times x to the n over n. Now, what we want on the bottom is an n plus 1, but we have an x to the n on the top here. If we integrate that by the power rule, we'll get x to the n plus 1 over n plus 1, and then our denominator will be correct. So let's do a little bit of correction to this Taylor series so it looks more like what we want up here. First of all, if we had, instead of an x, a negative x, then we would be able to pull out a negative 1 to the n, which would cancel with this negative 1. So if we have the natural log of 1 minus x, then we'll get the sum from n equals 1 to infinity of negative 1 to the n plus 1, and then negative x to the n becomes negative 1 to the n times x to the n, all over n. And then if we do negative 1 to the n times negative 1 to the n, that cancels out, and we're just going to be left with a single negative 1 left, because negative 1 to the 2n is just 1. And if we want to get rid of that final negative, we can just put a negative side right in front of our natural log, just like that. So then all we're left with is the sum from n equals 1 to infinity of x to the n over n. Now let's take the integral on both sides. So we integrate the negative natural log of 1 minus x dx, do the same on the other side. So what we're going to get over here, we can use Fubini's theorem to switch the sum and the integral. So we bring this integral here all the way to the inside, and then 1 over n is just a constant. So we're going to get the sum from n equals 1 to infinity of x to the n plus 1 over n times n plus 1. And now over here, we're going to have to do a little bit more integration. But let's take a look at this for a second before we move on. What we want to do is get it so that this x to the n plus 1 goes away, we just get a 1. Well, if we evaluated x at the value 1, then we would just get the sum that we want up here. So we could think about evaluating this result at 1. What other lower bound could we use for this integral? Well, if we plugged in 0, because n starts at 1, every single term is going to have a 0 to the power of some positive number, which means we'll just get zeros coming out. So the 0 won't affect our answer, and this will still be equal to what we want. That means we can go back here and turn this indefinite integral into a definite integral from 0 to 1, just like that. And this way, we don't have to worry about plus c at all. So if we evaluate this, all we're going to get is the sum from n equals 1 to infinity of 1 over n times n plus 1. And again, the 0 is going to disappear. So now it's time to move on to this integral over here. To start out, we can substitute the inside u equals 1 minus x, just like that, and du becomes negative dx. Luckily, we already have our negative dx in this integral, so we're just going to get 1 minus 0 is 1, 1 minus 1 is 0, and then we'll get natural log of u du. And let's do this one using integration by parts. So if we figure out what are we going to differentiate and what are we going to integrate? Well, we want to differentiate natural log of u so that it becomes 1 over u, and then we'll integrate the 1 that we can multiply out front without changing anything, and then integrate that to become u just like that. So if we take this, we'll use these two factors, plus and minus, and this is going to be equal to u natural log u evaluated at 0 and 1 minus the integral of 1 over u times u is just 1 du from 1 to 0. Now let's look at each of these parts. To start out with the easier one, this is going to turn into u evaluated at 0 and 1. So 0 minus 1 is negative 1, but then remember we have a negative sign out here. So we're going to have a negative negative 1. This is just going to become plus 1. Now over here, First of all, let's look at this lower bound of 1. If we plug in 1 times the natural log of 1, that's going to be 0. Natural log of 1 is 0, so we don't have to worry about the lower bound. But the upper bound, what is 0 times the natural log of 0? Well, the natural log of 0 is negative infinity. So this is actually a 0 times infinity indeterminate form. And this is actually an improper integral. Instead of evaluating it at 0, we're going to need to take the limit as u approaches 0 of u natural log u. And in order to do this, we're going to want L'Hopital's rule. So let's leave the natural log of u on top, but then take the u and turn it into a 1 over u in the denominator, just like this. Now the natural log of 0 becomes negative infinity, 1 over 0 becomes infinity, so it's an infinity over infinity time for L'Hopital's rule. So we get the limit as u approaches 0. And again, because this is going from 1 to 0, this is going to be approaching 0 from the right, so this natural log makes sense. Then we're going to get 1 over u as the derivative on top, negative 1 over u squared as the derivative on the bottom. So this becomes the limit as u approaches 0 of negative u, which just evaluates to 0. So our entire thing here just becomes 0. This upper bound is just as negligible. So all we're left with is 0 plus 1, which gives us a result of 1. So in fact, the result of this sum, the sum from n equals 1 to infinity of 1 over n times n plus 1, using our natural log Taylor series and integrating, we've gotten that this sum is exactly equal to 1. And that is our answer.